Hello, and welcome to the final speedrun of today with me, Vince. So this final speedrun will cover powers and roots of complex numbers in IB Math. So let's jump right in. So first, how do we raise a complex number to a power? If we have a complex number a plus bi to a certain power, we can actually just expand this binomially if you remember from chapter 1. So this would be equal to a to the 4 plus 4a3b plus 6a2b2 plus 4ab3 plus b4. So that would be expanding the number. And now we have to determine what terms have the I in it. So this has no I, this is one I. This has two i's, so this would actually be minus 6 AB, and then this one has three i's, so this would be minus 4 AB, and then this one would have four i's, so it would return back to normal. So yeah, that's really how you would expand a complex number. Now the other question is how you find a square root. So if we need to find a square root of a number a plus bi. Well, what we actually want to do, say this is equal to c plus di, is we want to solve that a plus bi is equal to c plus di squared. And so we know this is c squared plus cdi, 2cdi minus d squared. And so now we can equate that a equals c squared minus d squared and bi equals 2cdi, so therefore we can find the values of c and d and of the original value of the square root. And it's the same for higher roots. So yeah, that's about it. So we'll jump now into some questions. So our questions, I'll do the even ones. And so the first thing we want to calculate is I to the 173 minus I to the 272 plus I to the 351, plus I to the 351 minus I to the 766. And this is it seems like a very hard question, but it's not. Because we need to remember that I squared is equal to negative 1. I cubed is equal to negative I, because it's negative 1 times I. And I to the 4 is equal to 1 again. So it goes in a circle. I to I squared to I cubed to I to the 4, and then back to I, if we keep on multiplying by I. So what we can actually do is we need to just find the remainder of these numbers when they're divided by 4, and it will tell us which step in the cycle they are in. So 173 divided by 4 should be equal to 1. So remainder 1, so that's equal to I. Minus 272 divided by 4 is equal to, 0, so that would be I to the 4, so this would be equal to 1. 351 divided by 4 has a remainder of 3, so this would be minus I. And finally, 766 when divided by 4 has a remainder of 2. And so this would be negative 1 minus 1 is plus 1. So this is actually equal to 0 since both i's cancel out and both 1's cancel out. So that one was pretty simple. Okay, on to the next one. We have 3 times I to the 2018 plus 2 times I to the 2019 over 4 times I to the 2020 minus 3 times I to the 2021. And we can use the same trick as earlier. Well, I to the 2018 divided by 4 is remainder 2. So this would actually be negative 3. So I to the 2019 has a remainder of 3. So this would be negative 2i. This would be equivalent to negative 2i. I to the 2020, 2020 is a remainder of 1 when divided by 4. So this would just be equal to 4. And finally, 2021 has a remainder of 1, so this would be equal to 3i. And now we've turned it into a simple complex number division. So we have negative 3 minus 2i times 4 minus 3i plus 3i, because it's a conjugate, over the absolute value of this number, which is simply 5 squared, sorry, the absolute value squared, which is 25. So this is equal to negative 12 minus 8i plus minus 9i, sorry, and finally plus 6. So all over 25, so this is equal to negative 6 minus 17 over 25. 17i over 25. And yeah, that should be the answer. Yeah, that's correct. Okay, so now on to the next question. So we need to calculate the following and check our answers. So first we have 1 minus 3i to the 4. And so as we said, we can expand this binomially. This is 1 to the 4 plus 4 times 1 to the 3, which I will just write as 1. Or I will just ignore the powers of 1 since they're irrelevant. So it's more of 4 times 3i plus 6. Remember, this is 4 choose 2 times 3i squared plus 4 times 3i cubed plus 3i to the 4. So that's equal to 1 plus 12i plus 18 times 3, 30, sorry, not 36, 54 I squared, but I squared is minus 1, so this would be minus 54. Um, 4 times 3 cubed, 54 times 3, 162. Is that correct? Yeah. So minus 162i plus 3i to the 4. Oh, sorry, no, this wouldn't be 162i. 4 times 27 is only equal to 4 times 27, 4 times 9, 36 times 3 is 108. So minus 108i. And finally, we add 3i to the 4. I to the 4, of course, being 1 again. So this is simply plus 81. So our final answer would be 82 minus 54 is 32 minus 4 is 28. 12 minus 108, so this would be minus 100, minus 98, minus 96i. Yeah, and that should be correct. Yeah. So for the next question, we need to solve, where is it? 1, oh, we actually missed the question, so I'll go back to that after this. 1 plus I to the 5 plus 1 minus I to the 5. So what would this be? Let's, what would be the best way to do this? Should we just expand it? Yeah, I think we should just expand it. So this would be 1 plus 5i minus 5 choose 2 is 5 times 4 over 2, 10, minus 10 minus 5 choose 3 is also 10, so minus 10i plus 5 minus I. Oh, plus 5 plus I. I believe this is correct. And then plus 1. We start off with minus I this time. So 1 minus 5i. And then we have minus 10. Plus 10i, I believe. because this would be minus I cubed times 10. Yeah, plus 10I plus I to the 4. This would be 5 minus I. Yeah. And so we can see what parts cancel out. These two cancel out, these two cancel out, and these two cancel out. So we're left with 1 plus 5 plus 1 plus 5. So 12. Oh, actually, we're only left with a whole number. So it's 12 minus 20, which is negative 8. So I think that should be the answer. Let's just check. Negative 8I, of course. I must have missed out an I. Is it an I? Hold on. I don't think this can be. No, it's definitely not I. I think the textbook is wrong. Unfortunately, simply because we know the first term needs to be 1 in each case. Yeah, so I think it's just negative 8. Okay, let's go back to the question that I missed. So unfortunately, I missed the question. So the question was, we need to get the sum of k is equal to 1 to 1010 of I to the 2k minus 1. So the odd numbers of I divided by, I think this is phi or pi, k over 1010 times I to the 2k. So if you don't know what this pi symbol means, it means that it's the product of all of these numbers. So we need to get I to the 2 times I to the 4 times I to the 6, and so on. And this looks pretty tricky, but I don't think it is. So let's evaluate the top first. What would this be? Well, we know that I to the 2k minus 1 will only produce odd numbers, and we're alternating between even and odd. And so let's just see what is it for 1? I to the 1 is just I. And then what's it for 2? So I to the 3 is negative I. So the sequence will go something like this. And since we're ending on an even number, this will actually just evaluate to 0, I think. Yeah. Why would it just evaluate to 0? That's interesting, though. Why would the book make us solve this? But that's not for us to question. Let's look at the bottom part. So we need the product. So when I is 1, we're getting I squared, which is negative 1. So we're getting the product of negative 1 times negative 1 times 1 times negative 1, and ending on an even number. But so we actually need to count how many negative 1s are there. And since we end on 1010, that means we multiply negative 1 505 times. So this is actually just going to evaluate to 1. So we have 0 over 1, which should be 0. But the book is giving me a different answer, and the book says 1, and I'm interested in why it says 1, since this sequence should simply be I minus I plus I minus I plus I minus I. So I don't know, I think the book's wrong. I've been experiencing a lot of errors with the actual answers given in the book. So it could be that that is just the case. Anyways, let's move on to the next question. So we need to evaluate the following so we need to find the square root of negative I. Well, we know we can express this in the form of a plus bi. And so we can say that negative I is equal to a plus bi squared. In other words, this is equal to a squared plus 2abi minus b squared. So, well, let's equate real and imaginary parts. So we know that a squared must equal b squared, since 0 equals a plus b. And we also know that negative I is equal to 2abi. So Yeah, negative I equals 2abi. So this means that I times 2ab plus 1 is equal to 0. And since I is not equal to 0, 2ab plus 1 must equal 0. So 2ab equals negative 1, ab equals negative half. And since a squared equals b squared, a squared equals b squared. So in this case, it means that a must be the negative value of b, since we have a negative number and we're multiplying two numbers together. So this is equal to like a squared, negative a squared is equal to negative 1/2. So a squared is equal to 1/2. And a is equal to 1 over square root 2, or root 2 over 2. So the two, or actually, I mean, this could technically be plus or minus root 2 over 2. So going all the way back up, I think there are two possible answers. One of them is that root 2 over 2 minus root 2 over 2i. And the other one I think is negative root 2 over 2 plus root 2 over 2i. I think both of these would work as the square roots. Yeah, and that is correct. Okay, so for the next one, we have root 5 over 36 minus I over 3. And we need to evaluate what this will be. So again, we can say this is equal to a plus bi. And so therefore 5 over 36 minus I over 3 is equal to a plus bi squared, which is equal to a squared minus 2abi. Sorry, I mean plus 2abi minus b squared. So what do we have here? We know a squared plus b squared equals 5 over 36. And we know that 2abi is equal to negative 1/3 I. So in this case, we can divide both sides. So we can say 2ab is equal to negative 1/3. And I guess a is equal to negative 1 over 6b. Is that a fair statement? Yeah. So we can substitute that back up here. So we have negative 1 over 6b squared plus b squared is equal to 5 over 36. It's nasty. So we have, what is this? 1 over 36 b squared plus b squared is equal to 5 over 36. Let's multiply everything by 36b squared. So we get 36b to the 4 minus 5b squared plus 1 is equal to 0. Can we factor this out? Yes, we can, question mark. Did I make a mistake? That looks okay. Oh, minus b squared, of course, yes, sorry. So that was a problem. This should have been minus b squared. And so over here, this should be minus b squared. And this should be minus b squared. And so we actually have 36b to the 4 plus 5b squared minus 1 is equal to 0. And this is now factorable since this is equal to 9b squared and 4b squared. Which one is negative 1? This should be negative 1 plus 1 equals 0. So we have two possible options. We have one case where 9b squared equals 1, and therefore b equals 1/3. And another case where 4b squared is equal to negative 1, which is impossible, since b should be equal to a real number. So if b is 1/3, then what is a? So we know that, well, what can we use? 2ab equals negative 1/3. So 2ab equals negative 1/3. So in this case, a must be negative 1/2, I believe. 2ab, 1/3, so this is 2 over 3a is equal to negative 1/3. And so a is equal to negative 1/2. So that's one possible answer. But I'm pretty sure, let me just look over this formula again, because I might have got something wrong. 4b squared is equal to negative 1. B squared is negative 1/4. Yeah, this can't be a solution. But I have a feeling that this can be plus or minus since, sorry, where did I go? 9b squared is 1, so b is actually plus or minus 1/3. So we have the option to have a as equal to 1/2 as well. So the final answer should be, the number is equal to plus or minus 1/2 minus 1/3 I. Yeah, that should be it. Yeah. So on to the next problem. So we need to show that, okay, sorry about that, I had to go do something. And so now we are on to question 4, and we need to prove that the conjugate of a number to the power of n is equal to that number to the power of n's conjugate. This is looks like a proof by induction. So we would prove the base case first. N equals 1. The conjugate of a number is, simply equal to the conjugate of a number. Sorry, the number to the power of 1, which is the number, is equal to the conjugate to the power of 1, which is fine. So that's base case. Excuse me. So next, we need to prove for a number. Well, assuming it's true for n, we need to prove it for n plus 1. So z to the power of n plus 1 is equal to z to the n plus 1. It's conjugate, right? But we know that this is equal simply to z to the z's conjugate to the n times z to the conjugate, I believe, is equal to z to the n plus 1. But we know this is actually equal to z to the n conjugate, and we're simply multiplying it by the conjugate of another number. And it's a conjugate identity that if you have like two numbers like zw, the conjugate of the product is equal to the conjugates of the multiples of the conjugates of the individual numbers, and that's a proof for another day. But more or less, it allows us to say that z to the n plus 1, that this is equal to z to the n plus 1, which is exactly what he needs to prove. So that is the proof. So next, we are given that z is equal to 1 plus I. We need to find values of z so that z to the n is only imaginary. Okay. So we know 1 plus I to the n must be an imaginary number, so there must be no real term. How would we do that? Well, I guess we could just go through all the values. So we have 1 plus I, we have z squared, which is equal, of course, to 1 plus 2i minus 1, or otherwise, yeah, wait, this is just 2i, right? Yeah. This is just 2i. Z cubed is equal to 2i times 1 plus I, which is equal to negative 2 plus 2i. Yep, and z to the 4 is equal to negative 2 plus 2i times 1 plus I. And this would be equal to negative 2 minus 2 with negative 4. 2i, it would just be equal to negative 4, I believe. So z to the 5. And we should see this cyclical pattern because of I. We would assume that z to the 6, let's just jump to z to the 6. This would be purely imaginary, since this would be -4 times z squared, which is 2i. So -4 times z squared, 2i is -8i, of course. So for all values of n, where n modulo 2 is equal to 0 and n modulo 4 is equal to 2. Actually, sorry, this top one is irrelevant, but n modulo 4 is equal to 2. That would be our values of n. Finally, on to the last question, where we have 1 minus I to the 2n plus 1 is equal to 1 minus I to the -2i to the n. For all natural numbers, we need to prove this. Okay. Well, we know this is equal to 1 minus I to the 1 minus I to the 2n. So we can simply cancel these out. So this would cancel out. So we're left with 1 minus I to the 2n is equal to -2i to the n. And we can simply simplify this into 1 minus I squared, we're taking the square root of n on both sides, is equal to -2i. And that's about it. We know this is true. This is actually just 1 minus 2i plus 1. Minus 1. And so we know that that must be true. Yeah, so that's all for today's speedrun. I hope you enjoyed the speedrun. I hope that you learned a lot about complex numbers and their powers, and I hope to see you in the next speedrun. Ta-ta.